And today I'm going to be solving a couple proofs using contradiction and mathematical induction. The first proof I'll be solving today is a proof by contradiction. I was asked to prove that there is no rational solution to the given equation x squared plus x plus 1 equals 0. So let's assume the contrary and say there is a rational solution to the equation. And let's let x equal p over q, where p and q are elements of all real numbers, and p over q is in its reduced form. So let's go ahead and plug p and q into our equation to get p cubed over q cubed plus p over q plus 1 equals 0. Now we're going to go ahead and multiply through the whole equation by q cubed. And we're going to get the equation p cubed plus pq squared plus q cubed equals 0. Now, let's go ahead and consider a couple cases about our given equation. If p is odd and q is even, then the left-hand side is odd, but 0 is not an odd number, which leaves us with a contradiction. If q is odd and p is even, then the left-hand side is odd, and we have the same contradiction as above. If both p and q are odd, we again have the exact same contradiction. And if both are even, then p over q is not in its most reduced form, which is not possible because earlier we stated that we assumed that it's in its most reduced form. So there is no case in our equation that doesn't result in a contradiction. So therefore, there is no rational solution to the equation x squared plus x plus 1 equals 0. So the next proof I'll be doing is a proof by mathematical induction. I was asked to prove that n times n plus 1 all over 2 equals the sum of all k's from k equals 1 all the way up to n for all natural numbers. So we're going to let p of n be the proposition to our given statement. The first step that we do in any induction proof is the base step. So in our base step, we want to show that p of 1 is true. So let's plug in 1 for n. And when we plug in 1 for n, we're going to get 1 equals 1 times 1 plus 1 all over 2. So 1 plus 1 is 2, times 1 is 2, 2 over 2 is 1. So 1 equals 1, and since we proved that both sides are equal to 1, this step does hold. So the next step we'll be conducting is our inductive step. So we're going to start by assuming that p of k is true. So using this assumption, we must now show that p of k plus 1 is also true. So p of k is 1 plus 2 plus 3 all the way up to k equals k times k plus 1 all over 2. And we're assuming that our p of k statement is true. So now we must show that p of k plus 1 is also true. So p of k plus 1 is 1 plus 2 plus 3 all the way up to k plus k plus 1 equals k plus 1 times k plus 2 all over 2. So if our p of n is true for some k value, and we can show that it is true for some k plus 1, then we have shown that our p of n is true for all natural numbers. So using our p of k, we're going to add k plus 1 to both sides of that p of k statement. So we're going to have 1 plus 2 plus 3 all the way up to k plus k plus 1 equals k times k plus 1 all over 2 plus k plus 1. And as you can see, the left side of this new statement is the exact same as the left side of our p of k plus 1 statement. And now if we simplify the right side using algebra, we're going to get the following statement: k plus 1 times k plus 2 all over 2. We can now see that the right side of this statement is equal to the right side of our P of k plus 1 statement. Therefore, if P of k is true, then P of k plus 1 is true, and by the principle of mathematical induction, P of n is true for all natural numbers. Thanks for watching.